Today we're going to finish up the course. This is the last section of chapter 5, and then the rest is up to you guys. Do the work and exams. Everything's due by 12:59 p.m. on the 14th of August. All right, chapter 5, section 6, definite integrals and areas between two curves. We're going to expand what we've been talking about. Up until now, we've only talked about one function, and we're looking for the area from that function to the x-axis. That's it, and in a certain bound domain. So the definite integrals, we're going to be using substitution using two ways. One way is what we did it by substitute, make it simple, and then at the end put it back in there. There's a second way we can do it. We can use substitution, change the function, and leave it that way. But if we leave the function as substitution, then we have to change the bounds of integration. And that's what these are saying. And we're going to look at both of those in these examples. So theorem 7 says substitution in definite integrals. If g prime of x is a continuous function, on some closed interval AB, and f of x is continuous on the range of g of x, so if g prime, the derivative of our internal function, if it's continuous, and f of x is continuous on the range, what does that mean? Continuous on the range of g. What's that? But what this means is we have a composite function, a compound function. We have a function within a function. The values of f depend on the outcomes of g. And since g prime is continuous, g has to be continuous over some certain domain, AB. Now, if that's true, then f of x has to take those outcomes and start from there. So it's the function within a function thing we did in the Fogg-Goffin algebra. If that's true, then we'll be using this formula a lot. The integral from a to b of f of g of x times the derivative of the inside function, g of x d of x, then that equals the integral from g of a to g of b of f of u du. We've seen these letters and these symbols before. What is du? What is u, first off? Where does u come from? It is a substitution, but in our equation, in our example here, what does u represent? G of x. So du is g prime of x dx. Example. So as you see here, this is what we define as du, and this is what we probably define as f of u. So let's look at, we're going to look at both of these methods of converting it, changing the bounds of integration, and then two, we're going to leave it as the substitution method. Example 1. Evaluate this integral from -1 to 1, 3x squared, square root of x cubed plus 1 dx. Does that satisfy our conditions that we need? Well, let's see. Remember, what we're trying to get to we're trying to get there. So let's figure out what our outer function is, what our inner function is, because u is g of x, and then the derivative of it. So what's our f of x? What's our outer function? The square root of x. Because the inside function has to be g of x. Remember, we're looking at f of g of x times g prime of x dx. So here's g prime, here's dx. So what's my g of x? It's the internal function, x cubed plus 1. So g prime of x would be 3x squared. Not for that one. That's only when we use the substitution method. But yeah, I see why you thought that, but no, because it's already g of x. So if we rewrite this, we get x cubed plus 1, 3x squared dx. From -1 to 1.
Do you still want to write g prime of x on the far right in terms of d of x? So like 3x squared times dx?
No, so somebody asked, no, we only do that when we're looking at the substitution method. We
Oh.
use du equals u prime d, or whatever it is, dx at the end of it. Because this is a function of x. We don't write dx afterwards. It's just what it is.
Okay.
So we have our substitution. Our substitution, we have our f of u. And our du, since it's du, now we put a dx behind it. Because this defines du. So far, so good. Now, according to our theorem, we have to redefine the bounds. So g of a, our bounds are from -1 to 1. This is a, and that's b. So g of -1 is -1 cubed plus 1, which becomes -1 plus 1 is 0. So our lower bound is 0. And our upper bound, g of 1, is 1 cubed plus 1 is equal to 1 plus 1 is equal to 2. So we have our bounds taken care of. Our function is the square root of u du. From 0 to this becomes u to the power 1/2 du. So what's the integral of u to the 1/2 power? Remember, we're using this. Un plus 1 over n plus 1 plus c. So whatever you have here, you add 1 to it. Whatever that becomes, you put it on the bottom also. So it becomes u 1 over 2 plus 1 over 1/2 plus 1. So 1/2 plus 1, which is 2 over 2, is u of 3 over 2 over 3 over 2 from 0 to 2. What happens to with the bottom number? Since it's a fraction, we flip it. So we get 2/3 u to the 3/2 from 0 to 2.
And why do you use the bracket again on the left side of the integral?
It's just, this just says habit. You don't
Okay.
have to. It just tells me that this is one contained equation. So I do it now because in this part here, I know I can now contain it all in here. So I start with the upper one, which is 2 to the power 3/2 minus 0 to the power 3/2. So we have 2 over 3. This becomes 0. So we have 2 to the 3/2 becomes 2 times 2 to the power 1/2. 2 times 2 is 4. 2 to the 1/2 power is square root of 2 over 3. And there's your answer. So there's where we use substitution, and we left it in substitution. If you can leave it in the substitution method, but if you do that, you have to change the bounds of integration. So let's do the same equation, and this time we're going to use substitution to get the antiderivative, and then switch it back, and then plug in the original bounds of integration. Hopefully we'll get the same answer. The original question, there's method 2. It was from -1 to 1, 3x squared x cubed plus 1 dx. We're going to use substitution again. We're going to leave the bounds of integration this time. So we have the square root of u du. So the integral of 1/2, we add 1, and whatever the exponent is, so it becomes u to the 3/2 over 3/2 from -1 to 1. Flip the bottom. Now, before I do the bounds of integration from -1 to 1, I put my u back. I substitute it back. Because as long as we go back to the original function, I can keep the bounds of integration that way. But if I keep it as a changed bound, then I have to change the a and b. Let's see if it changes anything now. So we have 2/3. On the first one, it's 1 cubed plus 1 to the power 3/2 minus -1 cubed plus 1 to the power 3/2. One cubed is 1. 1 plus 1 is 2. -1 cubed is -1. -1 plus 1 is 0. So that's gone. So the 3/2 exponent becomes, bless you, plus 2 to the first times 2 to the power 1/2. 2 times 2 is 4. Square root of 2 over 3. So it works. It's best to know both ways, because if one way just gets very cumbersome and long, but a lot of writing, go the other way. Typically, if you look at it, the substitution method, leave it as a u value, is usually shorter because you have less writing to do. All right, let's take example 2. A. Integral of pi over 4 to pi over 2 of cotangent x cosecant squared of x dx. What do you think this one? You want to switch it to use substitution and switch the bounds, or just switch the substitution and then work it out and then put the numbers back in? I'll show you why this one's easier to switch it over. Because if we keep it in this way, then we have to keep it in radian measures. But if we switch it to substitution and leave it that way and change the bounds, then we change it to integers, to numbers, which makes it easier for in the long run. So the first thing we have to do is figure out what is u. Out of these two functions, which one is u, and then which one is u prime? Or I said du, not u prime. Look at your cheat sheet of the functions. So is cotangent the derivative of cosecant squared, or is cosecant squared the derivative of cotangent? Right. Cosecant squared is the derivative of cotangent. So our u is cotangent x. But again, if you reference your chart, you'll see that the derivative isn't really cosecant squared, it's negative cosecant squared. So what we have to do, so our cotangent is our u, cosecant is our cosecant x dx. We can call that our du, but we need to have a negative inside there, because we need to have negative cosecant, which means we have to have a negative out in front. So we have to have a negative out in front here. So now we just have to find the new bounds of integration. For the first one, we take cotangent at pi over 4. What is cotangent with respect to sine and cosine? It's cosine over sine. So cosine pi over 4 over sine pi over 4, which are both radical 2 over 2, so it equals 1. So the lower bound is 1. And then we do cotangent at pi over 2. Cosine of pi over 2 over sine pi over 2 is 0 over 1, which is 0. Now you see how much less writing we have to do. We simply have to take the integral of u. What is the integral of u? It's u to the first power. So it becomes u1 plus 1 over 1 plus 1. So you see, just because we don't have to write cotangent or cosecant or whatever at pi over 2, it's a lot less writing. The less writing, the less chance of mistakes. So we have u squared over 2 from 1 to 0. And plug them in. So we have 0 squared over 2 minus 1 squared over 2. That's 0. So we have negative and negative makes it a positive 1 over 2. That's my area. So again, knowing both ways. In this case, it's much easier because we didn't have to do that much writing. And typically for cosine, or cotangent and tangent, it's easier if we convert them to sine and cosines first. Okay? All right, let's look at B. The integral of negative pi over 4 to pi over 4 of tangent x dx. Okay. We could try to use a chart, but it's a lot, remember, I said it's a lot easier whenever you have tangent and cotangent to convert them to sine and cosine. Sine x over cosine x dx. Because this way we can use, well, again, if you use your chart, you just jump straight to the answer, but we're deriving it. Remember, we're using what method here? Substitution. We can't use substitution if we only have one function. So in this case, we have sine over cosine dx, pi over 4, negative pi over 4, pi over 4. So what is our u going to be, and what's our du going to be? It's typically we use the bottom one because it'll make it easier to do a integral, make it an ln function. So the bottom's cosine. The derivative of cosine is what? Negative sine. Negative sine x dx. So we need to have a negative sign. That means we have to put a negative out in front.
Sir,
Yes.
how did you get u as cosine x? Shouldn't it be like 1 over cosine x if we're like substituting?
No, we're using just the bottom number.
Okay.
These are function over a function.
Okay.
All right. So now we have to change our bounds of integration. So we take cosine at negative pi over 4, and we take cosine at positive pi over 4.
Why do we have a sine x times theta? Negative.
Because we take a derivative of u. And u is a function of x. It was a function of x already. We don't. So there's if we did if f of x equals x squared, we always put just 2x because it's already a function of x. But since u is a function of x, and we take a derivative of it, then we have to put what we took a derivative of it. Because remember, the derivative is actually dx du over dx. We move it to the other side because we want all the x's to one side. That's where it came from. So what is cosine pi over 4? Radical 2 over 2. What is square root cosine negative pi over 4? Same thing. Because cosine is positive in the fourth and first quadrants. And what we have here is du over u. And we have a theorem earlier that says whenever you take the integrals from a to a, it's always going to equal what? Remember, what do these bounds represent? These bounds represent your a to b. Because we have the f of x, we have the x-axis, and we have the bound. So now we can find an area. What if a and b were the same line? What's the area of a straight line? 0. Yeah, so we know the answer is going to be 0, but let's work it out. So we know the answer is going to be 0. So what is the integral of du over u? Ln u. And that's the reason we shifted that way. Radical 2 over 2, radical 2 over 2. So we have ln absolute value of radical 2 over 2 minus ln absolute value of radical 2 over 2. is 0. It's the same value. So again, that was one of the properties we had earlier. That if you integrate in the same bound from A to A, it's going to be 0. Even though it didn't look like it from this, from negative pi over 4 to pi over 4. Which brings us to our next topic. Why is this function equals 0? If it's going from negative pi over 4 to pi over 4. That means we do have some width. How can it equal 0? Right. So if we look at the sign from negative pi over 2 to pi over 2, and the sine function. So it goes from -1 to 0 and then to 1. So the area of this one is negative. The area of this one's positive, but they're the same area. Let's say -2 plus 2 is equal to 0, or negative A plus A is equal to 0. So that's exactly what happens. Which brings us to this. Symmetric functions. Definite integrals of symmetric functions. Think back to algebra. We had two types of symmetries that we talked about in functions. Remember that? Odd versus even functions? What is an odd function? What does it look like? Or what is it symmetric about? No. Origin. Yes. Because if a function only has odd exponents and no constant numbers, then it's an odd function. If a function has even exponents and maybe plus or minus a constant, then it's an even function. You can't mix and match. You can't have a function that has odd and even exponents or an odd with a constant. So if it's odd, it's symmetric about the origin. Evens are symmetric about the y-axis. Why is that important to us? Because this goes from negative A to A, negative A to A. Theorem 8 tells us if f of x is a continuous function on a closed interval from negative A to A, then we have two things that can occur. If f of x is even, then the integral from negative a to a of f of x dx, because it's symmetric about the y-axis, is the same if I double it, but just take one side of it. Since both of these areas are going to be the same, I can just go from 0 to a and just double it. That's what it says. And then if the function is odd, then the integral from negative a to a f of x is equal to 0. So this is negative area, this is positive area, negative area plus positive area equals 0. Why is this important? Will it matter if we take it and cut it in half and divide by 2? No. Or multiply by 2? Not at all. We could have done this and get an answer, no problem. The problem is this. Once you determine that you have an odd function, then you know there has to be an x-intercept. Kind of like the intermediate value theorem. Then you know there has to be an x-intercept. Has to cross the x-axis somewhere. You have to find out where it is, and now break your interval and take them both separately. You have to find out where it's below the x-axis and where it's above the x-axis. Take them all separately, take the absolute values of them, and add those together. Or is there another way? Because we know this part here from a to negative a to c is going to be negative. Is there a way we can change the sign with this one? Because we know this one, since it's below the x-axis, it's going to give us a negative answer. Without using absolute values, how can we change that? C to negative a. Change the bounds of integration. If you change the bounds of integration, then you change the sign of the function. Yeah, so don't always believe that just because, like we had earlier, we had that the integral of tangent was from negative pi over 4 to pi over 4 is 0. Well, let's figure out why it's 0, because some parts above, some are below. Because if that's back to this one. What does the tangent function look like from negative pi over 4 to pi over 4? The tangent function it goes from -1 to +1, and it's an increasing function. Its period is pi over 2, negative pi over 2, but we're just taking it from negative pi over 4, pi over 4. So we know that this area is negative, this area here is positive, so it's going to cancel out. Again, if you know what the graph's going to look like, it'll help you all these things even faster. So that's why understanding the graphs is muy importante. From -2 to 2, x to the 4th minus 4x squared plus 6 dx. Now, if it's not odd or not even function, if it's a neither function, then you just go on like it's nothing. So for this one, what do we do? Is it an odd function or an even function? Or neither? What's that? It's even because all the exponents are even and we have a constant. So that constitutes an even function. Since it's an even function, we could make our work a lot less cumbersome by going, instead of from -2 to 2, we just take half of it from 0 to 2. That's all we're going to do. Because it's symmetric, no matter what bounds you have, you have to find the midpoint, and that'll be your halfway point. Because it's symmetric, the midpoint will always be 0. Because it's not symmetric if it's shifted to the right, it's not symmetric anymore. But it's not an even function, honestly. It is symmetric, but it's not an even function. Since this is a sum and difference rule, we can take the integral of each of these separately. What's the integral of this first one? x5 over 5. Next one is x3 over 3. X to 6. Okay, question. Do you know where I got 5 and 4 and all these from? Because it's +1. Right. Because we add 1, and that defines our equation. So this is 4, so it's 4 plus 1 is 5 over 5. 2 plus 1 is 3 over 3. Starting with 2. So we have 2 to the 5th over 5 minus 4, 2 to the 3rd over 3 plus 6 times 2 minus 0 to the 5th over 5 minus 4 times 0 to the 3rd over 3 plus 6 times 0. All of these are 0, so it doesn't matter. Two to the 5th is 32 over 5 minus 2 to the 3rd is 8. 8 times 4 is 32 over 3 plus 12. Now comes the algebra. We have to have LCD. What's the LCD? 15. So we have to multiply this one by 3 over 3. This one by 5 over 5. And this one by 15 over 15. Three times 32 is 96 over 15. 5 times 32 is 160 over 15. 15 times 12 is 180. $160 from $180 is 20. $180 minus $160 is 20. $96 plus 20 is 116 times 2 is 232 over 15. And that's my area.
Basically, what I'm asking is, in order for an function to be an even function, does it always have to have a constant?
No, an even function is just even exponents, or it's just a constant itself. Because if you think about it, what makes a function even? What makes a function even is symmetric about the y-axis. For example, this x squared is an even function. The line y equals 3 is symmetric about the y-axis. So that's an even function. So anything with an even exponent and or a constant is an even function. The only thing about it is constants cannot go with odd exponents. Odd, for it to be an odd function, it has only odd exponents, nothing else. Now, that's a fair, very fair question. Now we're looking at area between curves. So what we're going to look at here is we're going to have two functions. We're going to have f of x function, and we're going to have a g of x function. And we're going to look for the area between A and B. How do we know the distance between these two curves? Well, we know the distance from f of x to the x-axis is f of x. And we have to add it to this one. Well, since this one's below the x-axis, it means it's going to have a negative area. So if we have negative minus, it becomes a positive. So that's the height aspect of our function. And we still have delta x. And this is going to be our areas. Of course, yeah, it's sub k because we're looking at, as always, it's always the smaller intervals. Bless you. So as we have our delta x's, that happens. So our area has been derived earlier. We go from 1 to infinity, or 1 to n, eventually we go to infinity. We're looking for the areas, which is f of xk minus g of xk times delta xk. Those are the sums. What do we have to do now? These are the sums of each one of those. To find the true area, these are called the Riemann sum, we have to now find the limit as the partitions go infinitely small. And that means our summation of all of our numbers goes to infinity. So we go from f of xk minus g of xk delta xk. So what's that going to look like? The area, as this defined, the Riemann sums, is the actual integral from a to b of f of x minus g of x dx. And that's our formula that we'll be using. Here's a question. Would this function work if f of x and g of x were on the same side of the x-axis? Yes. Why?
If the PFX would actually subtract the area below PFX.
Exactly. Beautiful. Yes. Because the integral of f of x would find this whole area from the function down to the x-axis. This is f of x. And then the g of x would find the area underneath it. So to find the area between there, we have to subtract them. So we have to chop off this area here. So yes, so it worked no matter what. It's easier to see if f is positive, g is negative. It makes it much easier to visualize it. All right. Find the area of the region bounded above by y equals 2e to the negative x plus x, below by y equals ex over 2, on the left by x equals 0, and on the right by x equals 1. Now, that's just a lot of words, but it's telling us this picture. The function, it has to be above by this. So the higher function is, I'll call this one y1, and the second one y2. So y1 is equal to 2e to the negative x plus x. And y2, since e to the x, that's an increasing function, it looks something like this. Y2 is e to the x divided by 2. So it used to cross at 1, it now crosses at 1/2. And this one crosses the y-axis at 2. So here's from 0, and here's to 1. We want to know this area here. That's the area we're looking for. So we're looking at the closed interval 0 to 1. Go from 0 to 1. F of x minus g of x dx. So f of x was y1, 2e negative x plus x minus y2, which is e to the x over 2. Since they're different functions, I put them in parentheses. Do I need the parentheses? No, there's nothing changes in the first one. And since the second one is simply a monomial, nothing's going to change there except just the sign of e to the x. All right, so what we have here we have 2e to the negative x plus x minus e to the x over 2. So we take the integrals of each of these separately. What is the integral of e to the power negative x? Yes, but now remember, it has to be, if that's the integral, e to the power negative x, take the derivative of it. So if I had e to the power negative x, if that's my function, what's the derivative of it? Negative e to the negative x. So I have to have a negative in front of there. What's the integral of x? X squared over 2. Because right now it's just x to the power 1. And the integral of e to the x over 2 is just e to the x over 2. Going from 0 to 1. So I have negative 2e to the negative x plus here negative x squared over 2 minus e to the x over 2. So the first one, I have negative 2e to the power negative 1 plus 1 squared over 2 minus e to the 1 over 2 minus negative 2e to the power negative 0 plus 0 squared over 2 e to the 0 over 2. So we have negative 2e plus 1/2 minus e over 2 minus e to the 0 is 1, so it's negative 2. That's 0. This becomes minus 1/2. Is negative 2e plus 1/2 minus e over 2. Distribute the negative, so it's plus 2 plus 1/2. Negative 2e minus e over 2. 1/2 plus 1/2 is a 1 plus 2 is 3. And then if we wanted to, we can combine these two. Give me LCD of 2, so it's negative 4e over 2. So it's negative 5e over 2 plus 3. Oh, I forgot something. My bad. This is a negative 1. I can't combine them. Because it's going to be negative 2 over e plus e over 2 plus 3. Woo. So now we can't combine them, so we just plug in the calculator. Yeah, it's 0.905. Because they're all numbers. All right, let's look at another example. Because then we're going to switch them around. Find the area. Of the region enclosed by y equals 2 minus x squared and y equals negative x. There's a function y equals negative x. What we need to find are the x values of where these functions intersect. Because it wants us to find the area between those two. How do we find that area? How do we find these points? That's where the two graphs are equal, right? So here's y1, y2. So if we set y1 equal to y2, where they intersect is going to be those 2 points. So y1 is 2 minus x squared, and the other one is negative x. It's a quadratic equation. What does that mean? What does that tell us we have to do? No. How do we set it up? Yep, get everything one side. Since it's negative, let's move everything else over there. So subtract 2 and add that. So we get 0 equals x squared minus x minus 2. See if we can factor it. X squared is made of x times x. The second sign is negative, which tells us what? The signs are opposite. And the bigger number is going to have the negative sign. That's a 1. So 1 times 2 equals 2. So what times what equals 2? When we subtract them, it equals 1. 2 and 1, 2 and 1. And the bigger number gets the negative because of that. So my answers are negative 1 and 2. Those are my bounds of integration. So the first function is 2 minus x squared minus negative x dx. Negative 1 to 2. 2 minus x squared plus x dx. Negative x squared plus x plus 2. Now we can integrate each one of those. The integral of negative x squared. Very good. The integral of x. Very good. And the integral of 2. 2x. Very good. From negative 1 to 1, or negative 1 to 2. Negative 2 cubed over 3 plus 2 squared over 2 plus 2 times 2 minus negative 1 cubed over 3 plus negative 1 squared over 2 plus 2 times negative 1. Negative 8 over 3 plus 4 over 2 plus 4. Negative 1 over 3 plus 1 over 2 minus 2.
Sir,
Yes.
one question before you continue. How did you get which one was the f of x and g of x, like within those two equations?
Good question. Very good question. Because we're looking for the difference of the two. The higher equation is always f of x. The lower function is always g of x. Very good question. Because you're subtracting them. If you did it the other way, then you'd get the difference of the infinities, so it wouldn't work.
And knowing which one is the higher and lower is by us graphing it, correct?
Yes. Or if you don't want to graph it, once you find out what the bounds are, you could pick a point between there. Like I would take a value of 0 and plug it into both of them. I'd have 2 here and 0 here. So this one's higher because at 0, this one's higher. And there's the functions are not going to change beyond that. So let's see what we have here. So we have negative 8/3 plus 2 plus 4 minus positive 1/3 positive 1/2 minus 2. We could remove the parentheses. Negative 8 over 3 plus 6. Combine those two. Distribute that. Minus 1/3 minus 1/2 plus 2. 8/3 minus 1/3 is 7/3. 6 plus 2 is 8 minus 1/2.
Since it's negative 8/3 minus 1/3 would be 9/3. Negative 9/3.
Oh, you're right. Good point. Good point. 9/3. Good catch. Good catch. I just lost the track of that negative. So it's 3 plus 8 minus 1/2. 11 minus 1/2 is 10.5. Now let's see if I messed up anywhere else in there.
It will be
it would still be -3, so it's 5. $4.5. I don't know, I'm brain dead. Very good. Good catch. It would be 4.5. You have 8 minus 3 is 5, minus a half is 4.5. Ooh, yes. Let's do one more. And then we're going to do something else that's kind of tricky. Find the area above by y equals radical x, below by the x-axis, and y equals x minus 2. All right, so there's that one. Below by the x-axis, and the line y equals x minus 2. So it crosses at 2. And we only want this area here, because it's bounded by the x-axis. So what's this other bound point here? How do we find that one? Yeah, where the two lines equal each other. So here's 1, 1, line 2. So square root of x equals x minus 2. Get rid of the x as the radical, square both sides. So x is equal to x minus 2 times x minus 2. X squared minus 2x minus 2x plus 4. Subtract x from both sides. 0 equals x squared minus 5x plus 4. They're both going to be the same signs, but the second sign's a plus. They're both going to be minus. What times what is 4? When you add them, you get 5. 4 and 1. So x equals 4 and x equals 1. Gotta be 4. So now we have everything we need. We can look at it, there's actually 3 ways we can do it. The first way, we could do this first part from f of x to 0, from 0 to 2. Then we can do the second part from 2 to 4. But when we do that, we're only going to take this difference in here. All right, so let's look at that. So the area, if we look at it from 0 to 2, It's only the area of our function, square root of x. It's under this area. That's area 1. Area 2 is from 2 to 4, and it's f of x minus g of x. So we have x to the power 1/2 dx. And we're going to add these two together. Plus from 2 to 4. F of x is the square root of x minus the function x minus 2. That's this one. Zero, 2 to 4. We get x to the power 1/2 minus x plus 2 dx. Integrate the first one, we get x to the power 3/2 over 3/2 from 0 to 2. X to the 3/2 over 3/2 minus x squared over 2 plus 2x from 2 to 4. You get 2/3. 2 to the power 3/2 minus 0. We have 2/3, 4 to the power 3/2 minus 1/2 4 squared plus 2 times 4 minus 2/3, 2 to the power 3/2 minus 1/2 2 squared plus 2 times 2. Again, I told you all day one, most of this class is going to be nothing but algebra. So 2/3, 2 to the 2/3, as we figured out earlier, was 2 square root of 2 minus 0. That doesn't do anything. Now, if we have 4 to the power 3/2, we can do the square root of 4 first and then cube it. So it's 2 square root of 4 is 2 cubed is 8. So it's 2/3 times 8 minus 1/2 times 16 plus 8 minus 2/3 2 square root of 2 minus 1/2 times 4 plus 4. We have 4/3 square root of 2 plus 16/3 minus 8 plus 8. They cancel. 4/2/3 minus 2 plus 4. (16/3) those cancel. 16/3 minus 2 over 1, the common denominator. The answer is 10/3.
Minus two, I thought it was. Oh, negative two. Oh.
Again, it's all mostly algebra in this class. Everybody okay with that? Now we're going to change directions. Integration with respect to the y-axis. Instead of taking dx, we're now going to take dy. Instead of having vertical columns, we're going to have horizontal columns now. Since we're looking at with respect to the y-axis, the outer one will be my f of x, my inner one will be g of x, because now I'm going to take these areas. These are going to be delta y's. Make sense? So now you have to think sideways. So our area is going to look like this. Instead of A to B, we're going to go C to D. F of y minus g of y dy. So what does this tell us? It tells us not only do we change the integration of with respect to y, but we also change the bounds of integration. The example we're going to do for this one is one we just did, example 6. It said above by y equals square root of x, below by the x-axis, and y equals x minus 2. So as we know, our graphs look like this. That's what we had in number 6. Now we have to change directions. here, when x is 4, what's y? 2. So our bounds of integration are from 0 to 2. We have to change our equations. Solve for x. And then our second one. Y plus 2 equals x. Remember, this is f of x, this is g of x. So now we have f of y minus g of y. This is original. Remember, what happens now? This is f of x, this is g of x. How is it going to change? What's f of y now? Since we're integrating with respect to y, what's the outer function? This is the outer function. So this is f of y. This is the inner function. It's g of y. Because you have to look at where we're going to take these rectangles. The outer one minus the inner one. Let's look at it this way. So our f of y is y plus 2 minus y squared. So if we integrate these, what's the integral of y? Integral of 2 y. Integral of y squared.
Do we want to do a implicit differentiation here, or is it not needed?
No, because we're not doing differentiation. We're doing integration. So in the first one, we have 2 squared over 2 plus 2 times 2, 2 cubed over 3 minus 0 over 2, 2 times 0, 0 cubed over 3. All these are 0. We have 4 over 2 plus 4 minus 8 over 3. So we have 6 minus 8 over 3. 18 over 3 minus 8 over 3 is 10 over 3. Same answer. Well, would it be anything different? Shouldn't be. But if you notice, it's a lot less work. It's a lot less work doing this way. Well, I say you got to change your mind. But if you look at the steps, super easy. Nothing difficult about it. as opposed to having to go through all of this. So why do we show you integration with respect to y? It may be easier if you have a convoluted picture like we just had. I mean, if you're looking for this area, it's pretty convoluted. This is so if we just did it this way, then it's just a different function. Much easier. There's a third way we could have done it. This is 2. And we know that this one here is 2. What if we took the integral of this function from 0 to 4? From 0 to 4, what would that give us? So that would give us 2 over 3 times 4 3/2 minus 0 3/2. So 0. So we have 2 over 3. The square root of 4 is 2. 2 cubed is 8, which gives us 16 over 3. Okay, what's wrong? I did the whole thing here. We don't need this part. So what's the area of this part? Well, it's not g of x. This is just a triangle. It goes from 0, so it's 2 units high, 2 units wide. It's cut in half. So 2 times 2 divided by 2 is 2. So if we subtract 2 from that, so if we subtract 2, so we have 16 over 3 minus 2 over 1. We get the same answer. Which one's the easiest out of the 3? I think I like this one. Because there's no transferring of x and y. This is not easier. So use whatever you know, whatever you do, algebraically, geometrically. If you know any shortcuts, knock yourself out. If it works, it works. But just don't do what I did, make a bunch of careless sign errors. End of section, end of chapter, end of course. You guys succeeded. Now comes the hard part, doing the work. And thank you. I really enjoyed the semester. Actually, it went really quick. And thank you for putting up with me, even though a couple of times we went way over the time limit. But you see why I did it. So we'd have to do part 1, part 2, just keep on going all the way through. So now you have just over 2 weeks to get everything done.
At the beginning, you said we're gonna have the final in person. I thought maybe I was wrong about that, but is the final just online, like the same as our other exams so far?
Yeah, I was thinking about that. What I'm thinking of doing is making the final is just the average of all your exams. Because again, we're learning all this stuff in 5 weeks. So that's what I'm thinking to do is your final exam will be your final exam grade. Well, I'll tell you what, take the final exam. If you take the final exam and make a higher grade than the average of your tests, I'll keep the higher of the 2.
We do pretty well.
If you do well on the 4 chapter exams and your average is high, then yeah, keep that. But yeah, but if you have made some errors there, and you think you can do higher in the final exam, then do that. But either way, I'll check both grades and keep the higher of the two. All right, guys. Thank you much. Thank you, everybody, for a great semester.